Now we are going to see how to design a Butterworth bandpass filter for high frequency applications. Okay, how to design a Butterworth bandpass filter, and you know that in high frequencies uh, you have to first identify what is called as insertion loss. Insertion loss occurs is a parameter which is of significance at high frequency, because insertion loss means whenever you are going to insert any component, what is the signal loss I am going to have because of that. Ideally, insertion loss has to be zero. Practically, because when you're inserting a lossy component in between your device, insertion loss value will not be zero. It will be be close to, it must be as low as possible, 0.1, 0.2, it should be like that. The insertion loss is very high, which means that the device is dissipating a huge amount of energy as heat. Okay, so the insertion loss formula is given. It depends on the load resistance ZL. So if you take ZL as 50, you can find the non-normalized values are given for the particular filter they have given. So the values are, two values are there. I am taking the upper value, 132.986 is going to be the load impedance for the filter. And the frequency, you see, it is 400 megahertz. My bandwidth is 5 megahertz. So the center frequency is 400 megahertz and total bandwidth is 5 megahertz. So it will be varying from 395 to 3. It is 2.5 on either side. So it is 397.25 to 402.25 megahertz. And I am creating an RF filter structure. And you see, same thing what we did. I'm getting a frequency range from 370 to 410 megahertz. I'm finding the S parameters and I am plotting this S parameters. Okay. So I will just run section by section so that you will understand how the filter will actually look like. See the frequency response of the filter. S11 is going to be the reflection coefficient in this graph, and S21 is going to be the actual transmission coefficient. So at 400, you see, you have close to 0 dB. 0 dB now 1. So whatever you send is transmitted. And at the same frequency, 400 megahertz, if you find this value, you find this value at 400 will be minus 10. Minus 10 means at 400, the reflection coefficient is very, very less, which means all signal which is transmitted is being sent to the output. So this is the RF plot object. So RF plot will plot the magnitude response, frequency versus magnitude. Our design frequency is 400. You see, you're getting a perfect flat band at 400. Okay, that is what I said.